So welcome everybody to the last week of our 2022 HPC user training. We're ending it with a big bang with some NVIDIA technologies, which are always exciting and innovative. And I want to thank everybody for participating, for contributing to this program. And we'll be pinging you later for feedback on the program to assess not only its benefits, but what we could do better because we're doing it next year. So with that, I'll turn it over to Christopher Kuipert, who is an NVIDIA Senior Solutions Architect, and Zoe Ryan, who is a Solutions Architect at NVIDIA. And with that, Christopher, you have the comm.
All righty, cool. Well, let's get right into it here. So yeah, Zoe and I are both on the higher ed team, and we're also both mentoring at your awesome hackathon going on right now. Do we have any hackathon attendees in the audience? I saw Andy at least, I know, is mentoring.
Oh, well, thank you, Christopher and Zoe, for mentoring, and other people who are here, Andy.
Awesome, yeah, having a lot of fun there and kind of just getting started here. So yeah, so today we're going to talk about clearly using NVIDIA GPUs with Python. So this course, you're actually kind of our alpha testers. Zoe and I made this course fresh. We've been working on it for the last month and a half here, updating it with the latest and greatest information. So, you know, we're really excited to finally share it with such an awesome audience here. So we're going to start with a brief overview of GPU computing. I did get a chance to look at Andy's slides from last week, and I saw that you got a pretty good introduction to GPUs, GPU computing, and even a bit of CUDA, which will be particularly useful when we talk about Numba a bit later. But we're still going to, you know, just make sure that everyone's here on the same page and talk a little bit about some of the programming models for GPU computing. Next, we're going to be talking about accessing the workshop materials. So has anyone here ever participated in a DLI before, an NVIDIA Deep Learning Institute course? NVIDIA DLI. Cool, okay, Marty, we got at least one of them, right? Okay, so anyone who's attended a DLI, you'll find this is a really familiar user interface. So we're gonna be using basically cloud computing resources through an NVIDIA developer account today. So I'm going to go ahead and post it in chat. You can kind of run through this in the background. Everybody is going to need a free NVIDIA developer account in order to access the workshop materials today. So, you know, you might want to sign up for that in the background if you don't have one already. It's a really nice account to have for a number of reasons, you know, forums and user forums and bug reports and all that jazz. But anyway, after we get a hold of the materials and get used to the environment, we're going to talk about three main tools today, and we're going to kind of start with an introduction. So those three tools are going to be CuPy, which is basically a drop-in replacement for NumPy. We're going to talk about Rapids, which is GPU-accelerated end-to-end data science. And then we're going to talk about Numba, which is an awesome just-in-time compiler tool that you can add into your Python stack to get really good performance out of the GPU and even write some custom more CUDA-like kernels. Right. So after we introduce all three of those tools, each one is going to have a notebook associated where we kind of run through some basic hands-on exercises. And then to finish out the workshop, we actually have an end-to-end example, a case study. It's, you know, a mock problem, a geospatial nearest neighbor search. And we're going to start with, you know, a CPU-based implementation, which, you know, if you can guess, is going to be pretty slow, right? And we're going to walk through basically applying all of the tools that we learned about in this workshop to basically accelerate that example end-to-end and get some really massive speed-ups. All right. So first, again, just a shallow dive into an overview of GPU computing and why it's worthwhile to you know, be here and take the time to invest to you know, optimize your code for GPU even. Right. So clearly, right, NVIDIA is centered around this graphics card GPU accelerator, right? And NVIDIA has been around since 1993. So originally, right, we're doing lots of computer graphics and, you know, accelerating, you know, the Pixar movies of the day and the early video games. And that continues to still be a big focus of NVIDIA, right? Making more and more realistic graphics, ray tracing, things like deep learning, super sampling, right? And that side of the company is certainly very fun. But if you think about just the raw amount of compute power that's needed to push some of these graphics, right? I mean, even on I'd say a low-end monitor today is a 1080p monitor, which has a couple million pixels, maybe updating 60 or 120 times a second. That's a lot of computation, right? So in the early 2000s, along with the advent of these things called programmable shaders, folks found out that you could use these GPUs for more general purpose computing, right? So applying it to molecular dynamics simulations or physics, climate, weather, right? So that's really taken off over the last 20 years or so, and we see more and more people, gravitating to GPUs for accelerated computing. And then finally, right, the big thing in the last decade or so, the big boom has been in artificial intelligence, and really NVIDIA GPUs are really kind of the hammer and chisel of doing AI, right? And the reason for that is because a lot of this AI training, it breaks down to dense linear algebra and matrix multiplications and computations that GPUs just really excel at, right? So those are kind of the big three areas that GPUs are pushing forward. Okay, so again, really high level, a CPU versus a GPU. Right, so a CPU is more optimized for serial tasks, right? It may have inside a laptop somewhere between maybe two to four, maybe even six cores, right? It'll be pretty snappy at computing serial processes. But a GPU, on the other hand, is really optimized for parallel tasks, right? Many more cores than a CPU, hundreds or thousands of cores. And while on an apples to apples basis, right, an individual GPU core is much weaker than an individual CPU core, just through the sheer amount of number of them that you have, right, the number of processing elements, you can get some really huge throughput gains and do math really quickly, right? I mean, it kind of looks like a giant matrix, right? Okay, and when we're programming for GPUs, the good news is the GPU and the CPU really work together, right? The GPU is an accelerator, because if you look at a code, a scientific code, for example, there's a lot of multi-million line Fortran codes out there, of which if you run through an example problem, the majority of the computation time might spend 95% of its time in a relatively small percentage of the code, right? Maybe 5% of the lines of code. Those are going to be things like maybe calls to BLAS libraries or solvers, dense linear algebra. So the idea with the GPU acceleration is those are the sections of code that you target for GPU offloading, right? The rest of the sequential code or things with a bunch of branching or all those types of operations, you leave them to the CPU, and you really just target those sections with high arithmetic intensity and port those over to the GPU. So minimally invasive, I would say. Okay, and again, you've probably seen these charts before, right? The reason that people are actually taking the investment into GPU computing is because it's really unlocking new problems, right? If you look at these Moore's Law-like charts here that show the single-threaded performance of the CPU over the past few decades, right? Clearly, in the early 2000s, things have fallen off, right? The gigahertz, didn't get up to 4 and 5 and 6. It kind of stopped, and people started getting multi-core or using multi-core and parallelism in order to get better throughput out of even the CPU, right? Where a GPU really from the ground up is a beast for parallel throughput computing, right? And along with the advent of AI and being able to augment HPC with new AI algorithms, right? Even do things like replace or speed up PDEs with AI surrogates. It's really scaled out the scale and the just the magnitude of problems that we can tackle with computing nowadays. Right. So I saw last week with Andy's section there, you got to talk a little bit about CUDA for programming the NVIDIA GPU. I think I might have seen at some point, maybe a little bit earlier in some of the courses, some OpenACC and OpenMP, right? So the idea of incremental portable optimization, adding pragmas and directives, right? So these continue to be two ways that a lot of people are programming NVIDIA GPUs, right? If you have the time to invest to learn a lot about the GPU architecture, all the different memory levels and all the profiling tools that we have, CUDA is going to give you the most expressiveness and the best performance, right? Having manual control over moving memory, right? Manually controlling the threads that you throw at a problem, right? And then here in the middle, right, we have this incremental portable optimization, these directive-based and pragma-based approaches, which are going to give you some pretty good, decent performance as well. But the area that we actually have the most people investing at NVIDIA, which this kind of surprises a lot of people, I found, is actually in accessing the GPUs via the standard languages, right? So writing ISO standard Fortran, ISO standard C++, right? Nothing about a GPU in there, but getting acceleration out of the GPU, right? Using the NVIDIA compilers, and it can dispatch a lot of operations using CUDA libraries and getting really good performance out of the GPU, right? And this story also continues quite nicely for Python, right? With the kind of little caveat that when we talk about standard Python, we're really talking about NumPy, right? That the library that a lot of people download first when they're doing Python programming for any type of numerical computing, right? So we'll talk about that quite a bit today. All right, so at first glance, there's a pretty big gap between Python, right? Python programming and NVIDIA GPUs, right? So we think of Python, right? It has a ton of advantages, and there's a reason that not only data scientists are using it, but even people that are doing high performance computing are trying to get good performance out of it, right? People here today, right? Really high level, really interactive, easy to use. We have things like Jupyter Notebooks where we're going to be able to do, in our web browser, these hands-on interactive examples. Easy to prototype. You have automatic memory management. You don't have to really specify types that often. And the package management is pretty nice as well, right? Because there's so many libraries out there for Python. Almost every scientific domain has a dozen or so packages specifically for what you're doing, right? So with Conda and pip, we have a nice way to get access to those, right? These NVIDIA GPUs, on the other hand, right, on the previous slide, when we're looking at programming models, and when you talk about CUDA, we talk a lot about things like C or C++ or Fortran. Right, we talk about the idea of using a compiler, right? Sitting there and using a bunch of templates and waiting and grabbing a cup of coffee, waiting for the compiler to kind of chug through your code and generate an optimized version that's going to run performant on your system, right? And in general, high performance, right? Python we don't always use for performance, right? These compiled languages we often have to drop a bit lower there, right? So how do we kind of bridge the gap? So all of the tools that we're going to talk about today are going to broadly fall into one of these three categories. How they bridge the gap between all the convenience features of Python programming and all the nice low-level performance we can get out of NVIDIA GPUs, right? The first one you're going to see is JIT compilation, right? So typically Python, we use an interpreter, right? It's not compiled. We don't compile our script and then wait for an A.out file to binary to run and run that, right? So what JIT compilation does is it basically adds a compiler into the Python interpreter stack, right? We're going to mark up functions in our code and basically say, hey, this is something that's, it's really performance critical, right? And with the tools we're going to talk about, it's going to dispatch to a real compiler and actually, look at what data types we're using, maybe some of our input operands, and generate a machine optimized version of that function, right? The next thing we're going to see is these low-level language bindings, right? While we typically access NVIDIA GPUs via C and Fortran and C++, there's no reason we can't use bindings in order to access those same functionalities via Python, right? And then finally, we're going to talk about the idea of using CUDA-X libraries, right? Which is kind of an abstraction on top of these language bindings, right? The idea of using things like cuBLAS, cuSolver, cuRAND, all these NVIDIA optimized libraries that we again typically access through C and Fortran, but just basically wrapping those and calling them from Python, right? And it's going to be very, very straightforward with the tools we'll talk about through this workshop. All right, so before we get into it here, there are a few tips that I want to mention for successful GPU computing, and I saw a few of these that you went over last week as well. But these are kind of golden rules that are not only important when we're doing Python, they're really important in general, right? And whenever we're programming for the GPU. Okay. Now, the first one is minimize data movement to and from the GPU, right? What happens on the GPU stays on the GPU, right? And the reason why you can see from this diagram here on the right, okay? So today we're going to be working with a system that has these T4, NVIDIA T4 GPUs, right? And that GPU has a memory bandwidth, right? Access its own GPU memory at about 320 gigabytes per second. Right? Very, very fast. If memory is already on the GPU, right, the GPU can really crunch through it. But anytime we need to access data from host memory, right, over in DDR memory, DDR4 in the case of our system today, we're going to be going over this PCI bus, right, which is down to 16 gigabytes per second. Compared to the actual computational performance and the throughput available for a GPU, that's really like sipping through a straw, right? So we want to try to initialize data on the GPU when we can. We want to only copy stuff back into host memory when we absolutely have to, right? And I will mention that there are kind of ways to get around this or alleviate it in some sense. One thing you'll commonly see is this technology called NVLink, which basically allows multiple GPUs to talk to each other very, very quickly, right? So if you want to move data from one GPU to another, you can avoid going over that PCI bus, right? And you can almost treat it like one big address space. That being said, it still requires keeping stuff on the GPU, right? There's still the PCI bus if you need to go back to host memory. The next one, right, if it hasn't been clear enough, these GPUs are parallel processing machines, right? Any serial operations should be left to the CPU. That's not what the target is. You want to look for, again, the things that have higher arithmetic intensity, doing a lot of flops, chunky loops, dense linear algebra, right? Like I keep saying, matrix multiplications are a great example. We'll see some huge speed ups in the workbook here. Another thing, and this can really stand for CPU or GPU, but particularly for the GPU, anytime you use a reduced or a lower precision, you can get a lot better compute throughput, and you can even get improved memory bandwidth, right? So we have a lot of people, for example, in the quantum chemistry community, who have traditionally done double precision FP64 for everything, experimenting with things like using mixed precision iterative refinement, right, and maybe getting some answers in FP32 or even FP16 precision, which can be computed much more quickly, and then refine the answer up to a double precision accuracy, right? And then another thing to keep in mind for these GPUs is they're not just they're not just a bunch of cores. They actually have very high memory bandwidth, right? So we see 50 gigabytes here, CPU going to the DDR memory on the host. This is 320 gigabytes for our T4, right? Much higher memory bandwidth. And if you look at an A100 today, they go all the way up to 2 terabytes per second. And the H100 that's coming out is up to 3 terabytes per second, right? So very high memory bandwidth. So things like Fourier transforms can be very quick. Right. Third, the huge, very important one is, right, to stand on the shoulders of those before you, right? Take advantage of the very mature NVIDIA development ecosystem for the GPUs, right? We have a bunch of accelerated libraries on the order of 100 plus, and for a bunch of different scientific domains, right? Even it goes as far as, for example, quantum circuit simulation, right? There's a ton of different libraries out there. Another thing is, right, these profiling tools, if you look out there for, or you have ever had any training sessions on profiling, these are all compatible with our Python GPU tools we're going to talk about today. And then finally, keep in mind, not everybody needs to be a GPU developer. A lot of applications are already GPU accelerated, right? People aren't always aware of what's out there. So, in these slides, which are on the GitHub, by the way, for this event, you can go ahead and click this link to find our NVIDIA catalog, where we maintain, I believe, on the order of a couple of thousand of GPU accelerated applications in a list there. All right, any questions so far as we finish up the intro to GPU computing? Pause for just a minute here. All right. So next, we're going to work through accessing the workshop materials. Hopefully this goes smoothly. This is our first time going through this way, but first of all, I'll introduce the test system, which is going to be hosted by NVIDIA. In fact, I believe we're going to be technically using some cloud resources, AWS or Google Cloud underneath the hood. The system we're going to use today is going to be configured with 4 NVIDIA T4 GPUs, right? These are from our Turing generation, so they're kind of buddied up along like the Volta generation cards, right? Not too old, a couple years now. And the important things you're going to want to notice, first of all, the single precision 8 teraflops, double precision is not listed. And the reason for that is because this card, unlike our V100 and A100 and H100, it does not have hardware accelerated double precision, right? So we're sticking in single precision today, which is just fine, right, for the examples we'll be going through. And then the other big spec you're going to want to look at is the GPU memory, right? So 16 gigabytes, right? The GPU has its own memory space separate from the DDR RAM on your host, right? So we're going to have 16 gigabytes per card to play with, right? On comparison, an A100 goes up to 80 gigs. All right, so first of all, as I posted the link in the chat, hopefully folks, and apologies for not sending this as a prereq. There's this developer account that everybody will need to sign up for. It's free. I'm not sure if it actually has like a confirmation email. If somebody can, you might even just be able to put some random email in there if you need to. But it is a really good resource to use in terms of the developer forum and getting access to all of our software. So it's probably worthwhile to go ahead and check out what's available there. And then after you have an account there, and I'll pause here in a minute, we're going to want to go to this courses.nvidia.com/DLI event, which I'll type here. Okay, and you might need to log in again, even after you're already registered. You can click login on the top right there. And I'm going to wait till a couple of folks have confirmed that they're at this page, and then I'll go ahead and provide an event code, which we'll use to enroll in the course. So we'll pause now. Not sure what I put for display name. Cool, we got one ready for the event code, 2 ready for the event code. All right, so here's the event code. Event code is in the chat. All right, so I think it looked a little weird for me because I've already redeemed the code before. But can someone verify when you actually log in with that event code? Are you getting a splash page that looks like this one here on the right?
I'm not participating at the moment. I'm not seeing that anybody has put their hand up, so it's not clear.
Yep, I get course activity in progress completed.
If anybody is participating along real time, go ahead and just raise your hand or mark it by your name.
Are you getting something like this, Alexander?
Thank you, Alexander.
Yes, but empty. Oh, there's nothing under my courses. So start course. Start a course.
Christopher Cameron says that he sees his profile page, but not the class.
Not the class.
And Mal is getting a DLI. Yeah, just keep it in the chat, folks. This is great. So several people are trying to work along with you, but they're having some trouble. Shengji is also participating. Did you get in, Shengji? Do you see classes yet? More messages. Yeah, Sinclair is getting a DLI event error.
Okay. And Sinclair, is that after you click that enroll button there? Apologies, folks.
Hey, live demos.
Yep.
That's why we record things, so no
Yep.
problem. It happens.
Okay. Getting the error as well now. Okay, let's Zoe, I'm gonna start a chat with Josh from our DLI team real quick here.
Yeah, I'm thinking that, are you getting that after you've attempted to enter the code one time already? Or, because if we attempt to use the same code again, yeah, okay, if you attempt to use the same code again, that's when we see that type of error. Let me see if we can find
so try
where on the site the course is.
Yeah, so if you're seeing the error, it sounds like you can enter your dashboard again here then on the second attempt. Okay.
Christopher, do you have more lecture, or we could let Zoe start hers and then do the live demo after you're both done with lecture? I don't know how your presentation's coordinated.
You know what? That's a great idea. I could at least I could talk for a little bit. I think if
I can troubleshoot with Josh in the back if you'd like.
Okay. Yeah, that's a good idea.
And then if, excuse me, Christopher, Zoe, if you want somebody to test something, just put it in the chat and everybody will keep an eye on that. Those who
Sounds good.
All right, great.
Perfect. Yeah, we'll just circle around back in that section. Yeah, we can go a couple more slides. Okay. All right. So one thing I want to mention today is that all of the tools we're going to be using, CuPy, Numba, and Rapids, can all be accessed via the Rapids container, right? So this container is available on ngc.nvidia.com. This is our container repository, which has a bunch of containers for various GPU accelerated applications, pre-trained neural network models, a bunch of different frameworks. And if you either aren't set up to use containers or you want to try something else like Conda or building from source, Rapids also has this so-called release selector right on the Rapids homepage at rapids.ai. And it basically gives you this little wizard where you can click through, right, what version of Python or CUDA that you have on your system. And it will kind of spit out a little command there at the bottom, how to get it configured and installed, right? So kind of nice, everything's wrapped up in one place. In addition, you should have access, once we get the course all squared away here, you should have access to the materials for an entire year. You can log in and spin up the VM, so you can always come back and test something there as well. All right, so we're gonna just do an introduction here on CuPy first, right? So first of all, has anyone here used NumPy before? I imagine there's got to be a few. Awesome. Okay, cool. Yeah, so at the hackathons, I'll say from experience, the mentors tend to be pretty happy when somebody comes in with a NumPy code, right? Because we have this awesome tool called CuPy, which is basically a drop-in replacement for NumPy, right? Meaning that matching the same API as NumPy, right, the same function calls, we're able to get GPU acceleration in our existing Python code, right? So, so if anyone isn't familiar with NumPy, NumPy is one of the oldest libraries, one of the most well-developed and longest developed in the Python ecosystem. It's the first library that a lot of people download when they download Python, right? Especially in the scientific space, and it's used for doing math, right? So it particularly mathematical operations on arrays of data. Right, so the base data class for NumPy is the so-called ND array, which is going to hold data of some type, and importantly, it's going to be a homogeneous type of data, right? So CuPy, on the other hand, first of all, I'll mention that CuPy actually is not developed by NVIDIA, right? It's developed outside of NVIDIA, and of course, NVIDIA is it's open source on GitHub, so right, we help out with issues when we can and whatnot. But again, CuPy is a NumPy-like interface, right? So other than pretty much changing our import statement, right, we can use NumPy code with CuPy. We have explicit control over copying data to or from the GPU, right? We can copy those ND arrays, and just like we have a NumPy ND array, we have a CuPy ND array, which is almost the same thing, with the exception that it exists in GPU memory. right? So it's functionally very, very similar. You use it the same way, but it exists in the GPU. CuPy has data interoperability with, importantly, the deep learning frameworks, Rapids and Numba, right? So you can imagine maybe we're doing some pre-processing of data that we're then going to feed into a deep neural network. Since we have data interoperability, we don't have to worry about copying the data back to the CPU or anything like that. It uses highly tuned NVIDIA libraries underneath the hood, right? So if you're doing, for example, a matrix-matrix multiplication, it will be dispatching to cuBLAS or cuTensor under the hood. And if you want to get more advanced and write your own custom CUDA kernels, write your own custom functionality, you can do that in a Python API provided by CuPy as well. All right, I'm going to quickly check here. All right. Okay, so when I'm talking about how easy it is to port, right, and the API similarity, this is what I mean, right? In this case, we are creating this 4096 by 4096 matrix, and then we're doing a QR decomposition, right? Just a very simple NumPy function. Here we've ported that same code over to the GPU. The only thing that we changed has been highlighted in green, right? We changed your import statement to import CuPy as NP. The API is identical, right? And ran on the test system that we have today. We're getting a 52x speed up, right? Going from NumPy to CuPy with just changing that import statement. Now, for the remainder of this workshop, just to be very explicit and very clear, we are going to go ahead and import NumPy as NP and import CuPy as CP, right? So we can tell them apart, right? But in some cases, it really is easy, right? Some people will basically make some logic around their import statement. If a GPU exists on the system, import CuPy, otherwise import NumPy. Okay, let's check where we're at now. Yeah, this is where we want to jump into the hands-on. One thing that I could do is maybe run through the notebook myself. What are they before?
Actually,
sorry, I was seeing the same error when I attempted to use the same code again, but I linked in the chat to the dashboard, and I was wondering if anyone could confirm if they're seeing it listed under their courses in progress. It's titled Using NVIDIA GPUs with Python. No? Okay. It's interesting.
So Christopher, I actually think that's a really good idea, because that would, if you go ahead and do a full demo, we can capture that and it'll be a reference point in our recorded video. And then we could come back and see if people are able to actually do stuff. Would that work for you? That
would be perfect. Okay. Yeah. And like we said, we'll have access to the course for a year as well. So, but hopefully we get it squared away here. The DLI team's been very, very helpful. So cool. All right. So I am going to go ahead and we'll launch it here. So when folks hopefully do get access to this course, we'll be clicking this click here to get started link. And right, just like the regular DLI, if anyone's attended one of those, there will be some button here that basically says like start, right? And it will take a moment to spin up. That will basically reserve one of these virtual environments for you. And then you'll know it's finished when you get this nice launch button. Oh, what were they before and after conditions? So the code that I listed there was the complete code. So this is running on the system that we have today for the demo. So these are like some Xeon Platinum CPUs, and this is a T4 GPU. But I didn't. This was the coding completion. Yep. So that's the before and after import statement. Yep, perfect. All right. So yeah, we mentioned introducing the lab environment. So I saw one of your maybe week 7 or week 8, you had an introduction to the Jupyter environment. So I think probably everyone here is familiar with these Jupyter notebooks, right? Basically broken down into these text cells and code cells that we can modify, right?
Correct.
Yep, perfect, great. Yeah, so in this case, right now that we're we're on the demo system, we can verify the NVIDIA GPUs that we have in our system with this NVIDIA SMI command, right? In a Jupyter Notebook, if you have this exclamation mark prefix, it will redirect this to the shell. Okay, so we see that I have 4 Tesla T4 GPUs. We can see, you know, how much the power they're using, the utilization, right? They're all sitting idle right now. We can see all of their memory, right? As I said, 16 gigabytes, right? There's a little bit of stuff hanging around there. And then this other command that we can run through is NVIDIA SMI topo -m, which will show the topology of the system. This is where we would see things like affinity between the GPUs and the CPUs, right? In this case, we have only a single socket, so there's no special CPU affinity here. And this will also tell us what type of interconnect we have in between our GPUs, right? So in some cases, you'll see NVLink. The system we have today has 4 GPUs that are not connected via NVLink, so we're going to be traversing the PCI bus, right? And then finally, right, we can also query what type of CPU we were allocated, and you know, just to show that we didn't pair up with a weaker CPU here. This is a really nice Intel Xeon Platinum generation CPU there. All right. So next, working through the introduction to CuPy section, and let me check real quick if we had any. Okay, yeah. So introduction to CuPy. So NumPy is, as I said, widely used for numerical computing in Python. So right here is that a QR decomposition with a bit smaller size, right? And we can execute the cell, wait for NumPy to finish it. Right, and then we can run the same, right? Notice that all we did is change the import statement. All right, so pretty nice speed up, down from 140 down to 16.4 milliseconds there, right? So we already see a pretty good speed up with absolutely no code changes, right? Other than the import statement here for this relatively modest problem. Now, one thing you'll notice in the timeit function here, which, you know, timeit is a way to, in Python to time a command, right? And it will run it a few times so you get some type of average. One thing you'll notice is that in any of the GPU cells, we have this CuPy CUDA device synchronize call. Does anybody know why we have that? Any guesses? Don't read below. Anybody know why we're synchronizing with the GPU? Not quite. Yeah, so it has to do with timing, right? Yeah, so as it turns out, exactly, to make sure they're all finished, right? So it turns out that the CPU actually launches GPU kernels or GPU functions asynchronously, right? So the CPU comes to the spot where it says, okay, do this QR decomposition with CuPy, launch that kernel, right? And then the CPU is going to keep chugging along. It's not going to necessarily wait for that GPU to actually finish running the kernel that we told it to do, right? So with this CuPy, this CUDA device synchronize function, which is important not just in CuPy here, but also if you're doing CUDA programming, it's telling the CPU to wait until the GPU has returned and confirmed that it's finished the work that we've told it to do, right? So we're launching the kernel and then we're waiting for it to finish. If we didn't have that, we would get an inaccurate timing. We would get an even bigger speed up for the GPU, right? Because we'd basically just be measuring the kernel launch time, right? So you'll see that quite a bit when we're actually doing timings here, okay? Now, as I said, these NumPy typically operates on arrays of data, right? The base data type is this NumPy ND array, and CuPy implements a similar class called the CuPy ND array, right? And again, the big difference being the NumPy ND array is in the host memory, right? And the CuPy ND array lives over in the GPU memory. So there's a number of functions that we can use to basically transfer data from the host to the GPU or vice versa. Right, so here in this example in the workbook, we're showing creating a NumPy ND array of data, right? This little matrix. Here we're moving it to the GPU by calling this CuPy as array function, right? And we're just passing the NumPy ND array. Okay. Now we have a GPU, and this data structure is a CuPy ND array that exists and persists in GPU memory. Okay. Now that data is in GPU memory, we can manipulate it, right? We can perform operations on it. For example, we might want to take all the values and square them. Okay. And then we might want to take that data that we just squared and then do something with it on the CPU, right? We might want to feed it into some CPU only library or whatever, right? So we need to copy it back to a NumPy ND array, and we do that via this CuPy as NumPy function, right? So I can go ahead and execute that cell, right? So initially an ND array, boom, we squared it, then we returned it back as an ND array. Note that these NumPy and ND arrays are not implicitly convertible. Right, so if we call it a CuPy square function on a NumPy ND array, right, we're going to get this unsupported type NumPy ND array because that data is in GPU memory. Right. The next thing I'm going to share here is we can use CuPy to actually orchestrate multi-GPU programming. Right, so this cell is showing an example here where we're using this little with statement to choose a different GPU device. Right, so the GPUs are ordered GPU 0, 1, 2, 3. We're choosing the next GPU in the stack, GPU 1, and we're creating a CuPy ND array on GPU 1. Okay, and then we want to copy it from GPU 1 back to GPU 0. Right, we just call this as array function, just like we did when we were converting between NumPy and CuPy. Right, and now we have a copy of that data resident on GPU 0. Right. Finally, just to show a little bit of a speed up here, right, to what you might be able to achieve. This is a 4096 by 4096 matrix, A and B, and we're doing a matrix multiplication. This is comparing a NumPy versus CuPy. Oh,
hey, Chris?
yes. Yep.
Yeah. Okay.
Sorry, folks, I didn't see that. All right. I'll try increasing the font size as well. Let's pause here and see if people are actually able to access the notebook. Zoe, it looks like you're saying the code's working.
Yeah, we've extended. So there was a miscommunication on our side about when the course was. So Chris and I were able to access it because we had tried earlier in the morning, but it had expired by the time this started. So they added some additional time and you should be able to access it now. And if you get the error, like I said in the message, it will give you maybe potentially the DLI error if you tried to register already, but the class should still be there on your dashboard. So confirm in the chat if you're able to actually get it up and started.
Awesome. And I'll try making this font bigger. There we go.
Yeah, I was about to ask that as well. It probably comes out better on the recording if the font's bigger. Thanks for doing that.
Mm-hmm. Oh no. Sorry, folks. Okay. All right. Well, I'm going to keep marching along here, and hopefully we intercept a bit later here with folks able to log on. But you can see this really nice improvement in runtime, right? NumPy versus CuPy, we're dropping down from 22.4 down to 0.2 seconds for this matrix multiplication, right? So the GPU's strengths and computational throughput can give us some really terrific application speedups. But there are two types of overhead that I'd like to talk about that are important when evaluating your problem for acceleration on the GPU. Kernel overhead and data movement overhead. So we're going to jump back over here. Thanks, folks. All right, so the first type of overhead we need to worry about is so-called kernel overhead, right? And there's a couple different ways that this can manifest. The first one we're going to talk about is JIT compilation, right? So again, remember that Python does not use a compiler, right? If you do C and Fortran or whatever, right, we write something, we send it off to a compiler, we wait for it, and then we run the binary file. Python doesn't do that. It uses an interpreter that just kind of marches through, right? But as it turns out, that compilation, right, the time that it takes is used to generate optimized code, right? It may inspect things like, what type of function are you running? What is the size of your input operand if it's known at compile time? What data type are you operating on, right? What type of hardware or even optimized libraries are available on your system? And that's all information that can be used to generate a more optimal, better performing version of your function, right? So essentially, CuPy adds that compiler goodness via JIT compilation, right? So anytime we call one of these CuPy functions for the first time, there's going to be a check, and it's going to say, is this our first time calling that CuPy function, right? And if it is our first time calling it in a given execution of the program, CuPy is actually going to dispatch to a real compiler. It's going to compile and cache, it's going to actually compile, the function that you're using, right? After it compiles it, which is going to have some overhead, just like any compilation does, it's going to cache that compiled intermediate version of the code, right? So any subsequent calls of that function are going to use that pre-compiled version, right? In other words, you're only going to eat that JIT compilation overhead one time, right? The second type of kernel overhead that we see is so-called kernel launch overhead, right? And this has to do with the fact that we're launching some code, we're kicking some code off to run on the GPU, but we're using Python, right? So there's some overhead associated with marching down through the Python wrappers, right? Dropping down to the CUDA C level and calling the CUDA API, right? Then when the kernel is actually kicked off, there may be some interruption with the OS or even the CUDA driver, right? There might be some latency associated with launching the kernel. And then once the kernel actually makes its way over to the GPU, there can also be some overhead associated with the GPU context switching from another task, right? The GPU might be doing something else already, right? And it has to either stop or switch out from what it's doing to work on the task that you just sent along, right? Now, the cost of this kernel launch overhead is typically on the order of a few microseconds. And it's something that's going to be applied anytime that you launch a kernel, right? So what are some defensive strategies against this? Well, clearly, if we have to eat this kernel launch overhead every single time we launch a kernel, we want to reduce the number of kernel launches that we have, right? So one way to do that is, in some cases, we can increase the data set size, right? Increase the amount of number crunching that we're doing in a given function call, right? Another thing we can do is we can fuse smaller kernels together into so-called uber kernels or mega kernels, right? So as opposed to, say, launching 3 different kernels that are all doing some, maybe even operating on a similar data structure, we can combine those all into a single kernel and only eat that kernel launch latency overhead once, right? And as it turns out, there are some capabilities with CuPy via a decorator called CuPy Fuse that does let us fuse together smaller kernels, right? In particular, element-wise and reduction kernels. Another thing we can do is use CUDA streams, right? So CUDAs are, it's basically a way you can think of it to backfill the work queue or oversubscribe the GPU in this case. Throughout this course, have you used Python decorators at all? The syntax of adding like the little @ sign above the function definition? Don't think so. Okay. Use them before in Flask, right? Okay, so these are pretty similar, just the Python syntax. They're quite similar to pragmas or directives that you see out of, like Fortran or C if you're using OpenACC or OpenMP, right? The idea of not modifying the actual body of a function, but rather giving some hint or some attribute that will in some way change the function, right? So, OpenACC, we may say ACC parallel and ACC loop, and ask OpenACC or the compiler or the runtime to generate some parallel version of our kernel there. In Python, right, we have a similar idea with these so-called decorators. And for the syntax, we just add this little @ sign. The one we have in the workbook is CuPy Fuse, which is going to fuse together multiple element-wise operations. And then we're also going to talk about in Numba, this @JIT decorator, which will say JIT or compile this function. All right, so it looks like folks are still having, okay, good. Oh, somebody just got the course. Cool, people are getting the course, awesome. Great. Thanks, Zoe. That's awesome. Yeah, so with folks starting to get the course to show up, should be able to find a page that looks something like this. All right, you might need to click the course title, and there should be like a start task button over here. Oh, did we mess the title up? Yeah, that should be the course, yep. If somebody gets the launch button to appear, please let me know. Awesome. Yeah, they have these so-called hot labs set up that are basically like cached, waiting to start up quickly for us, so it should work. Alex.
Unfortunately, I don't think they have that set up since the time was wrong, so it might take a couple minutes. Yeah, sorry about that.
Oh, of course, yeah. Yeah, yep. So since there is a little bit of a mix-up issue, as Zoe was saying, you might be sitting for a while before that launch button appears. So with that, I'm going to go ahead and actually probably just finish out the CuPy notebook, and then I think we can intercept in the Rapids notebook. Would be a good place to do it. So hopefully this is big enough for everybody now. So here we go, kernel overhead, right? So in order to show the JIT overhead, what I'm doing is I'm just calling this determinant function 5 times via CuPy, right? And I'm just printing out the timing for every iteration. That was interesting. Here, let me try restarting the kernel. There we go. There we go. Beautiful. Yeah, first to run a cell gets a free donut. Awesome. Great. Yeah, so you can see here, right, I ran this determinant function 5 times, and on the first time it took, what, 0.7 seconds. And on the subsequent executions, it took, 0.005 seconds, right? And again, the reason for that, that's just exhibiting our JIT overhead, right? The next thing I want to show is that, recall that we have that kernel launch latency, right? The overhead associated every single time we launch a kernel. And that can really rear its ugly head if we're not doing a lot of work inside of a kernel, right? If we have a really small runtime. So in order to show that, we're doing this QR decomposition across a variety of different matrix sizes and comparing NumPy versus CuPy. And we can see here for these really, really small matrix sizes, 64 by 64, CuPy is a bit slower, 128 by 128. CuPy is a tiny bit slower, but as we start to get a little bit bigger, right, NumPy really starts to lag behind. And as we get into larger and larger matrix sizes, right, the CuPy time doesn't increase very much. The NumPy time increases quite a bit, right? Look at that for a 2048 by 2048, huge difference, right? And then finally, we mentioned that idea of this CuPy fuse function, right, which is a little bit more of an advanced topic, but it's useful for element-wise or reduction kernels, such as what we see here with this squared diff function. And here we're calling this with CuPy, right? So we have all these element-wise subtractions and multiplications. We're calling it both with and without the CuPy fuse decorator, and you can see a modest speed up. Here we go. Yeah, see, it's super fast. 88 for the non-fused version, down to 34 microseconds for the fused version. All right. Okay, so next, data movement overhead, right? The golden rule, what happens on the GPU stays on the GPU. Reminder that the reason for that is because while the GPU can talk to its GPU memory really quickly and crunch through numbers, anytime we need to access data from outside of the GPU's memory buffer, we need to go over that PCI bus, which is very, very slow, and it's basically like sipping through a straw, right? So a few considerations for data movement, right? So first of all, are we actually doing enough work to account for the data transfer overhead, right? If we have very low arithmetic intensity such that we're moving a lot of bytes, but we're not doing very many flops on each of those bytes, right? We may not be getting we're very likely to not get a performance advantage on the GPU, right? Versus just doing it on the CPU. Another consideration is, in some cases, can we even create our data on the GPU instead, right? This is showing an example of, doing some generic processing on a GPU. In one case, you can imagine first creating your input data on the CPU, then copying the data over the PCI bus over the GPU, and then actually doing your processing. On the other hand, what if maybe we're doing a random number generation, right, for our input data? We can create the data on the GPU. It'll dispatch to the NVIDIA cuRAND library, which does really fast random number generation, and now we can get right to data processing, right, and really cut that time down. Another thing to consider is, as you see with CuPy, we control the data movement to or from the GPU, right? So those CuPy ND arrays are going to stay on the GPU until you retrieve them, right, using those helper functions. So if you have algebraic functions that maybe have intermediate values that you can compute on later in your program execution, right, considering keeping temporary variables on there until you need to move them back. And then finally, we can consider overlapping computation with data movement with things such as CUDA streams, which is again a bit more of an advanced topic. Donut, please. Yeah. Yes, cuRAND does support setting the seed. It does. And while I'm not a huge expert in cuRAND, I know that it does like correct parallel random number generation, like in terms of the seeding, right? There have been a lot of libraries that like use the same seed and have a bunch of hash collisions and whatnot. All right, so the next section is data movement overhead. Right, so, yeah, sorry, I started executing, or I restarted the cell midway, so it's from time. I don't remember where perf counter is from. There we go. All right, so here we're just plotting some speedups for a dot product between two ND arrays, right, A CPU and B CPU. And in this case, we're initializing the data on the GPU, right, and doing the comparison. And you can see, right, we're at a 14x speed up on the GPU over the CPU. Well, what if the input data for that dot operation already resides in system memory, right? And we have to move that data over the PCI bus. This is where I would ask you to modify this cell and insert the CuPy code to basically do this dot product with the exception that the data is initialized on the CPU, right? So we can just go ahead and continue here to the solution, right? So right here, we're initializing the data on the CPU, and now we're copying it over the PCI bus. And our speedups that were 14x before, right? Are now quite a bit lower, right? So that shows how it kind of shift the mark, right? You need to always initialize and keep things on the GPU as much as you can, and always be cognizant of the data movement there. All right, next we're jumping over to notebooks are running, yeah. Next, we're moving over to managing GPU memory, right? So beyond just the overhead of that we talked about, right? The GPU has its own separate memory space separate from the CPU. So when we're working with it, we need to be cognizant of the fact that very often the host memory is going to be much, much larger than the GPU memory, right? These GPUs have 16 gigs each, right? They go all the way up to 80 gigs for a top class data center GPU. But in general, your host server might have, a couple hundred gigabytes or, even up to terabytes of memory, right? Furthermore, your total memory is going to be larger than your free memory, right? As you're doing computation on the GPU, we're going to be using and consuming memory, so we need some way to query the free memory available. We need to be able to determine whether or not our problem can fit in the GPU memory, and if not, we need to consider things like splitting our problem into stages, right? Processing the first half, moving it back to the second half, or even doing things like multi-GPU programming, right? And distributing the problem across multiple GPUs. Okay. Another thing we're going to talk about is unified memory. Did you get to talk about this last week in Andy's section? Unified memory? Really nice.
I believe I mentioned it briefly, but I didn't really talk about it. So you can,
Perfect. Yeah. Yeah, so unified memory is a really, really nice programming convenience feature that you can use with the GPU, right? So the idea is we have this, as we've talked so far, we have the GPU memory space, the GPU address space, And then we have the CPU memory and the CPU address space, right? Two very, very separate, distinct regions, right? But with unified memory, we effectively have a single unified memory address space, right? We can allocate things on the GPU, on the CPU, right? The existence of those objects are going to be known both on the CPU and the GPU as well, right? To show you an example, here's a situation where we're using unified memory, and we have some array that actually physically exists in the GPU memory, right? And we want to use it on the CPU, right? Maybe we're calling a NumPy function, okay? With unified memory, when we try to access that memory on the CPU, there will be a page fault, which will trigger the movement of that data from the GPU over to the CPU automatically, right? So essentially, we just have a single address space, right? A single pool that we allocate ND arrays via CuPy or NumPy, and we don't worry about if we don't have enough space on the GPU, right? And we don't worry about explicitly moving data to or from the GPU. It's all done implicitly with this unified memory. Now, certainly there is some overhead associated with that, right? I mean, if we know we're going to need this data on the CPU, well, when this page fault happens and then we have to roll back up the stack and move the data over, right? The CPU is going to be sitting here waiting, right? Or vice versa for the GPU. So there is some overhead associated with that, but it's a very convenient, it's very convenient for the programmer to not have to think about two different memory spaces anymore. Right. So, with unified memory, we can now essentially oversubscribe the GPU memory, right? We have 16 gigs on these T4s. We can work with a bigger data set and let unified memory swap the data pages in and out as needed. And it's a bit easier to program. And then furthermore, while I did mention that overhead, right, with the page fault, via CuPy, there's actually the capability to prefetch memory. Right, so if we know that we're going to need this data very shortly in the CPU memory, as opposed to eating the overhead of that page fault and waiting for that data to transfer, we can use this API to prefetch that data so it's there right when we need it. Right, so we can even tackle some of those performance issues. Great. All right, so we're going to really quickly going through the managing memory, GPU memory section here. Right, so. We're starting with showing a way to query the amount of memory you have on your GPU using NVIDIA SMI. This is what we used earlier at the beginning of the workshop to basically show the status of our GPUs. It's like a top command for GPUs, and it will tell us how much free and total memory we have in our GPU. We can also query that information natively with CuPy. Right, and just for good measure, since we haven't been careful about clearing things through this workbook, let's just clear all the GPU memory. Okay. Now, what happens if we try to allocate too much space on the GPU? Here's an example of making these CuPy ND arrays. This is a total of around 16 gigabytes of memory, and we have just a hair under 16 gigabytes, right? Technically here. So we will get this error out of memory, allocating this, right? And one solution, as I mentioned, is to switch over to unified memory, right? Then we can allocate as big a data as we need, and any of the data migration will happen implicitly. So here we're showing basically how to trigger or turn on unified memory via CuPy. Let's try that again. Try allocating those big arrays. Look at that. And we can certainly do any type of computation on those arrays. For example, we may want to add them via CuPy. But keep in mind, as I said, performance will take a hit as the GPU swaps pages in and out of memory. All right, so that's going to take a while to run, probably in the order of 20 seconds or so. But I'm going to keep marching along, make sure we stay on target here. A couple tricks in the bag that I want to mention, in addition to what we saw in the workbooks here. As I said before, CuPy is interoperable with other Python tools via a common interface called DLPack, right? So we can share CuPy with Numba, Chainer, Rapids that we're about to talk about, PyTorch. We can even use it with typical message passing with MPI for Pi. We can write custom CUDA kernels with CuPy. There is a basically wrapper around the CUDA runtime functionality, such that we can write raw Python CUDA kernels, right, and stay completely in Python land. And then finally, as I was saying, right, CuPy is compatible with Nsight profilers. We can even mark up sections of our code with NVTX, which makes it easier to interpret in the profiler system, right, completely interoperable with all those profiling debugging tools. If my GPU does not support NVIDIA SMI, do you happen to know if it would still support CuPy? So every GPU should support NVIDIA SMI, including the NVIDIA Jetson. So it may be that you don't have that the binary in your path, or maybe you don't have the CUDA toolkit installed. But yeah, good question. Came pre-installed. Yeah. Well, we can talk about that offline. Yeah, but every GPU should support NVIDIA SMI, right? And I just want to mention as we're marching along quickly, right? So we talk about CuPy, which is awesome, and sure, there's some multi-GPU support if we kind of, right? We showed how we can allocate data on different GPUs and launch different solvers if we wanted to and whatnot. But I do want to mention that NVIDIA came out with a new tool called cuNumeric, which is very similar to CuPy, right? The idea of being a drop-in replacement for NumPy, with the exception that while CuPy is really for single GPU, cuNumeric is for multi-GPU, and not just multi-GPU in a node, but also multi-node as well, right? So here's an example for a Navier-Stokes equation out of a CFD course that was on GitHub, where we changed the import statement for a code that was previously written in a serial fashion, and now scaling with weak scaling up to over 1,000 GPUs across a few dozen or so nodes, or probably a couple hundred nodes. Right, so there's this whole, it sounds like magic, right? There's this whole stack that comes along with this in terms of a static analysis of your Python script and does all of the task management and constructs a DAG and dependencies between all the tasks, right? So there's a bit on top of this, but right, in terms of the programmer perspective, it's really the same idea as CuPy, right? All right, moving into Rapids. Anyone ever used Rapids before? NVIDIA Rapids. Two packages we're going to talk about today are cuDF and cuML, if you've heard of those. Okay, we got at least one, cool. Rapids, yeah, so Rapids is a collection of tools. cuML, perfect. Yeah, we're going to be using that for clustering today. Awesome. So we got at least one person using it. Yeah, so Rapids is an end-to-end GPU accelerated stack developed by NVIDIA for data science, right? So you can see here pre-processing, machine learning, and graph analytics, interoperable with any of the deep learning frameworks, right? And the idea is just like we have CuPy for NumPy users, Rapids enables things like Pandas users, right? Or scikit-learn with a GPU accelerated alternative that matches the same API, right? And furthermore, with this Dask tool, which is for multi-GPU and node distributed arrays, you can actually scale out Rapids to multi-node and get really, really good performance that way as well. Right, so this is right. While you do see Rapids often talked about, right, for pre-processing data for neural networks and whatnot, it's really for anybody, right? So a lot of the same tools that we see in scikit-learn and Pandas that are GPU accelerated in Rapids are used by HPC practitioners or data scientists, people doing AI and machine learning, right? One example that I kind of like is you see a lot of people kind of mixing AI plus HPC, and a couple of the recent Gordon Bell winners and Gordon Bell finalists have been doing, for example, molecular dynamics on GPU, right? So those applications have ran historically on GPUs, right? They were some of the pioneers of GPU computing decades ago, right? Everyone does MD on GPU. But if you want to pre-process that data, well, if the trajectories or the information is already resident on the GPU, you can use Rapids, right, to do that pre-processing and not have to copy the data over. You might use something like cuML to do some type of clustering or some type of analysis. And then you may even take that same data that you used from the MD simulation and feed it into a neural network, right? So that's a pretty complex workflow, and every single piece of that is GPU accelerated with this open source free software. And you never have to leave the GPU. Okay, so again, the kind of yin and yang, right? What applications are being replaced here? So the two main ones that I'm going to show today are for Pandas for pre-processing applications and scikit-learn for machine learning applications, right? We have equivalents under Rapids called cuDF, right, which replaces Pandas, and cuML, which will replace scikit-learn, again, with a GPU accelerated variant. And you can see, right, a number of other ones for Viz and graph analytics and whatnot. In fact, there's a lot more than just what I'm talking about today under the Rapids umbrella. I just wanted to include this chart to share a few more of the more domain-specific ones and kind of show, again, the yin and yang, the CPU versus the GPU version for things like people doing graph analytics, which I know GPUs really, really excel at, geospatial signal processing, and then any image processing that all has GPU accelerated alternatives under Rapids. All right, so cuDF. cuDF, right, was created under this whole idea that the average data scientist is spending 90% of their time actually wrangling their data, right? ETL operations, extract, transform, load, and then the fun stuff, right? The actual research, the creating models or analyzing their data is generally much less, right? On the order of 10% or so. So essentially wanting to GPU accelerate that upfront ETL portion so we can get to the fun stuff more quickly. Right, so as I said, this is a GPU accelerated drop-in for pandas, right? So just like pandas has the kind of base data structure is this so-called pandas data frame, we have cuDF data frames that are pretty much the same thing, except they are resident in GPU memory, right? Underneath the hood, cuDF is using an optimized CUDA C++ library that has a bit of additional functionality on top of standard cuDF, but right, you're getting a good performance there. And right, pandas typically looks something like this here on the right, right? It's used for tabular data, and it's one of the most popular packages out there in Python. Right, so using cuDF, right, again, drop-in replacement. So what does it look like? Here we're showing a simple example where we're reading in some type of data set, right? Like this is quality of a bunch of different red wines, and then maybe calling some type of method on that data set, right? Maybe we want to call a head or a tail to examine the first 5 or last 5 elements of that data set, right? Very cheap operations, but if we want to do this with pandas as opposed to doing import pandas as PD, import cuDF as PD, and we're off to the races. Okay, we mentioned the data interoperability with other packages for CuPy, same story for Rapids. And now we're going to jump into the cuDF notebook. So let's see how we're doing in terms of people being able to access the notebooks. It sounds like most of the people have that kind of figured out here. People who haven't given up. Yeah, so we're going to be, hopefully you have this like Jupyter Hub interface. We're going to be jumping into Notebook 2, which is the Rapids introduction. Anybody able to navigate here and run through the cells? Awesome. All right, we're going to pause for about 5 minutes here to let folks work through the cells here. This is pretty much just a hands-on part to get used to using pandas and cuDF. Yeah, so it's only going to run on Linux. So I'm not sure if it works, if you've heard of like this WSL, Windows system for subsystem for Linux or something like that. Yeah, it might work there. I'm not sure though, but that might be the one thing to try out. Sinclair asks if we'll have access to this course after today. Yeah, so assuming we had all our bits in the right place and all the flags set right, you should have access to this course material for an entire year. You can jump back into this course for a whole year. And also the notes, the slides here are on the SDSC event page, the GitHub where all the other event or lecture notes have been.
All right, so are we ready for Zoe or are we taking a short break?
Oh, yep, just taking maybe 2 more minutes for folks to work through this
Okay.
PDF section. Yep.
I had to step away. Okay, so did we stop recording during this part? No, we're still recording. Okay.
Yeah, 2 more minutes. I'll jump to the next. next part here?
I didn't, Mary. We'll work with the recording because sometimes you forget to turn it back on when it's brief breaks.
Right.
All right, sorry for rushing folks along, but we're going to keep marching here. And again, we'll have access for a year to these results. Yep, you got it, Alex. That yeah, that looks like that cell 9 did not hide for whatever reason. I'll have to figure that one out. Working out the bugs here. So moving to the next section in the stack, we're going to talk about cuML, which is for GPU accelerated machine learning. Okay, right. So the motivation here is, and the reason a lot of people use scikit-learn, right? These data sets are getting bigger and bigger, especially as we're intentionally making them bigger to feed neural networks and whatnot. And with bigger data sets comes the need for more performance solutions for analyzing the data, right? Whether it's looking at distributions, some dimensionality reduction, sampling and clustering, right? So a lot of the things that we typically use scikit-learn on the CPU in GPU land here, right? So this is an example for a DB scan, right, which is a clustering algorithm we can see in scikit-learn, right? You can see here we're, in order to create our initial data set, we're creating a pandas data frame, right? So this is all on the CPU. And then we're calling that DB scan function via scikit-learn. That same function, that same type of script, GPU optimized, right? We already talked about using cuDF in place of that pandas data frame. Right? We didn't change anything at all, just that import statement or the the namespace there, and then likewise for cuML with a clustering algorithm, right? And now we're running on the GPU. Okay, there's this shows some of the different classes of algorithms that are available in cuML. The big ones that I see a lot of people doing are clustering and classification, right, and linear regression. We also have XGBoost, right? So XGBoost is the one that a lot of people use to win those Kaggle competitions. Really popular ML method that is GPU accelerated in cuML as well. And now we're going to take maybe just 4 minutes to work through, or to start working through the GPU accelerated machine learning with cuML section, right? Which is we have that nice divider line there. We're still in notebook number 2. I'll resume in 4 minutes here. All right, thanks everyone. Marching along here. Make sure we get to all the content. Next, we've got Zoe to talk about Numba, and then we'll get to the end-to-end example.
Awesome. I'll go ahead and take over the screen share if that's all right. All right, are you guys seeing my screen all right?
Yep.
Yes.
Okay, perfect, thanks. So at this point, we've gotten a good introduction to both CuPy and Rapids, and we're going to just change gears a little bit to a Numba introduction. At this point, it's a good thing to keep in mind that like at the end of this introductory work, we'll be going through one example problem like Chris had mentioned at the top of the hour, where we are actually going to use all three of these tools. So Numba, in case you guys haven't used it, has anyone actually used Numba before? I don't know, this is like, I feel like a little less popular of a tool than CuPy, but it does have great support on both CPU and GPU. So there's the potential to use it in a couple different ways. Awesome. Okay. So these are kind of the three takeaways, the three things to know about Numba before you get started. We've talked a little bit about just-in-time compiling already. Numba is at a high level a just-in-time compiler for Python functions. Like I mentioned, this can work, the target can be your CPU or your GPU. So if you're actually trying to take code you have in Python and eventually migrate it over to the GPU, a really nice intermediate step can be to use Numba to port it to a just-in-time compilation for your CPU and then move it over to the GPU. In a similar vein, Numba is an opt-in only kind of compiler. So you don't have to have all of your code in a Python script or workflow that you want to move over to Numba. You just specify specifically what functions you want it to compile, not the whole program. So not everything is a perfect candidate for Numba, but if you do have parts of your code that are, the opt-in option is really nice. And then like we've talked a lot about already, the nice thing about Numba, CuPy, and Rapids is they work really well together within this PyData ecosystem, which is just one term for basically things that work well with NumPy data types and which involve you just staying in the language Python that hopefully you're really comfortable with. So Numba is just kind of another extension we can add to our already growing Python ecosystem. A thing that we will see as we go through this, it's really awesome that you already had that really in-depth CUDA C++ training before, is Numba gives you kind of a lower level look at writing Python code for the GPU. You're accelerating it at kind of a kernel level, but you don't actually need to go out there and learn CUDA C++ if that's not something that is worth it in the time that you have. So it will give us some lower level optimization tools, but it does mean it's a little bit more involved in some of the examples that we've looked at so far. Let's see if we can move to the next slide. There we go. Okay. So the first thing that we're going to talk about are Numba ufuncs. You guys are probably familiar with, the way Numba can create ufuncs. NumPy has tons of ufuncs already built in, universal functions, which are really useful. But if you've ever tried to go ahead and write one of your own, you might know that the implementation is trickier and involves using C and C++. But Numba gives us kind of a clever way to mimic the functionality of ufuncs and create our own custom versions of them. So I have two categories here, and there are two categories you're going to go through on the notebook as well. One is a decorator vectorize, and one is a decorator at GU vectorize. The decorators, which Chris had mentioned a little bit before, we'll see just kind of top our Python functions. That gives us the option to opt in to using the Numba compiler. So we can see on the left, vectorize is kind of a more simple version of GU vectorize. We are operating on scalars only. We are compiling a pure Python function into a ufunc, which is kind of the way we're replicating what NumPy actually does to create ufuncs. You're able to operate over that huge data input, usually a NumPy array, very, very fast. And what Numba is actually doing is generating the surrounding loop, allowing us to do that iteration in a very efficient manner. So the main key difference to take away from vectorize and GU vectorize is that vectorize is slightly simpler, whereas GU vectorize can operate on higher dimensional arrays. So we know that NumPy does really well with data types that are multi-dimensional arrays. And so having GU vectorize gives us the opportunity to create fast Numba ufuncs that operate on those higher dimensional inputs. The return statement we'll see looks a little bit different when we use GU vectorize. we actually kind of pass in an output array that is then filled during our function, and then we get back that same array. So that's another difference that you can see if you look at the documentation as well for vectorize and GU vectorize. So you'll see this code in Notebook 3. We're going to take a second to look there after I show you just an example of what you'll see in the code. So here we're actually creating just a relative difference vectorized number function running on the CPU. And then we do something a little bit ugly just to see a chart of how our performance changes over time and the benefits we see of using this vectorized decorator with our function. So the NumPy version is the traditional version where you can see in linear fashion, we get slower as our array size grows. And then NumPy starts to outperform that NumPy original implementation even more when we scale up to bigger array sizes. So that's a common theme for today. Anything GPU accelerated does really well when your data set or your data input grows. Numba will show that time and time again. So we can go ahead. I guess we'll go over this too. One thing that's important to note about Numba, which is maybe a little bit different than CuPy, is that the GPU support is relatively new, but is growing extremely fast. So one thing I wanted to note before you kind of started looking at the different Numba code that we have is that these features are growing, but they're not all inclusive. We don't have everything that we have when we were working in Python. So if you're ever looking at something you have implemented already and you're wondering if that's something that Numba can support, just go ahead and look at the documentation, because even I feel like in the course of making this content for you guys, new things were added and new things were changed. So just keep that in mind as you're thinking about porting to Numba. It's an ever-growing ecosystem, especially on the GPU side. But we do have kind of some really things that will do really well on the GPU have already been implemented. And that's, I think, a good thing to keep in mind, like built-in types, a very extensive NumPy support. And we also have standard math libraries as well, one of which is math and CMath, which we will use a lot in the course of today. So we're gonna shorten down the sections of going through the notebooks because we do have a big problem at the end, a big work through we wanna go to. But if you guys wanna take a look at the Numba vectorize and GU vectorize section, it's just the same work that we were just showing with the graph on the previous slide. So you can go ahead and take a look there. I'm just gonna give you like 2 minutes or so we can get on to the next content. All right, I assume that's not enough time, but like Chris had said, we can always come back to this content later. And I do urge you, if you get more interested in porting your Python code to one of these, CuPy or Numba, to come back and revisit these examples because they are a great place to start. So I think you might have seen almost this identical slide in the previous week, so I'm not going to take too much time on it. But like I mentioned before, Numba provides us kind of a lower level look at the detail we kind of get with CUDA C++, we can get close to in Numba by writing our own customized kernels. You can actually go ahead in CuPy and write customized kernel that actually use CUDA code, but in Numba, we're able to write it in more of a Pythonic syntax. So just as a quick refresher, I don't want to take too much time on this because you already got your CUDA course for the week. Here we have our basic thread hierarchy, which is something we definitely want to take advantage of when we're looking to get our most performance solutions using Numba. A CUDA kernel is something that as a function that is executed on the GPU. We have the same thing that we have in CUDA C++ as we do in Python, the same terminology at least. Everything is executed by different parallel threads, not just one at a time. And then we here in the diagram have a group of threads which build up to be a block. And a group of blocks build us up to be a grid. So I believe this is a diagram you guys have seen before. And then a kernel in turn is executed as a grid of blocks, and those blocks are made up of threads. Another key thing to know here is each block is executed on by an SM, a streaming multiprocessor, which often you'll see in custom Numba kernels that have been written. That SM value is declared and used when trying to describe how many blocks and grids we'd like to use. So that's just like at a high level, what we should keep in mind. A nice thing about working in Python and the Python environment is that if you want to just see some basic speedups, you don't actually have to think too much about this basic thread hierarchy. Nothing that Chris was showing relied on this knowledge. And even so far, using vectorize and GeoVectorize in Numba don't require us to have a lower level understanding of kind of the hardware we're working with. But if you're looking to get like near C++ or CUDA C or C++ implementation speeds, then having an understanding of this and how it builds is pretty important. So now we're transitioning over to kind of focusing on Numba as a GPU option. Like I've said before, we have a lower level kernel development option without actually having to leave Python. So we're looking at kind of two before and after what changes. You'll see this time and time again. Like I said, this is a good first step and second step as for porting your code over to the GPU. You take advantage of the fact that Numba works well on the CPU, and then you can go ahead and try to replicate that in a GPU version. I think that's worked really well for me in the past. So we have a couple key steps here on the bottom. We're initializing our data, or we're copying it over to the GPU. Of course, whenever possible, initialize your data on the GPU and keep it there as long as possible. We're getting that lower level support for actually writing our own implementations of kernels. Like we've said previously, we're still doing that just-in-time compilation, which gives us fast execution as we run it more and more times, just paying that one-time price for doing the compilation at the front. And then this is something we're going to go into even more, is the ability to move data around and work with other libraries. I think this slide is a little boring, but it is a really good list of the ways in which we can engage with the CUDA array interface in libraries that you're probably already using. So we haven't touched too much on like machine learning, deep learning, but I think that the presence of GPU accelerated Python is really growing in that space. And frameworks like PyTorch use the same array interface, which is another really good entry point for using Numba, using CuPy, and using Rapids. So if you see something in that list that you are already using in your Python workflows, then you know that the underlying kind of basis, the standard protocol is the same for those libraries as it is for Numba. And that gives you a really easy way in with the data types you're already using. So I think this is a good selling point for the whole presentation and for all of this kind of GPU development within the Python ecosystem, because it gives you all these options for getting into, whether you're working on something like signal processing and using cuSignal, or you are using PyTorch, a much more well-known library. So this is just a little pitch for all the places that you could go ahead and try to use Numba, CuPy, and Rapids. So this interoperability we're focusing on in the next section. Let's see. If you guys want to click through that section, I'll go ahead and give you 2 minutes again to take a look. And if there are any questions in the meantime, you can drop them in the chat as well. Okay, we're going to go ahead and bring it back to the presentation and look just at a couple more examples with Numba, excuse me, before we jump into that final problem overview. So something you'll see a lot within CUDA examples, you might have read the blog post, which I feel like is maybe one of the most popular of 6 ways to do Saxby with different languages, different GPU accelerated options. Here we have on the right, just for those of you who are more familiar with CUDA C++, or for those of you wondering how different it really is from these implementations we're looking at with Numba, we have a side-by-side comparison of workloads doing this just basic Saxby calculation, something that's easily GPU accelerated. You can see on the right-hand side where we have the Numba, we're giving it our data types as well in the input, and we're targeting the GPU by putting that target set to CUDA. And then we have obviously the same type of calculation happening within the 2 kernels on the left and right. On the left, you can see there's just more overhead in controlling things like your block ID and your block dimension and your thread, all of which are fairly common if you've used CUDA before, but are again things that require you to have just a more extensive CUDA C++ background than the code on the right does, even though we're still writing a custom kernel. And then at the bottom, we just show the 2 different methods in which you can actually go ahead call these Saxby kernels that we've written above. So you can see that there's some slight differences in how we call it. The right is much more Pythonic, obviously, because we're able to just call and return our resulting array value, whereas we're required to have some extra steps when we launch CUDA kernels in CUDA C++. So we'll skip that section. It just again shows you the same code that we're looking at here, but you can go ahead and run it for yourself on the notebook if you'd like, especially while I continue to talk about the next examples. We also have included a custom Numba kernel for matrix multiplication in the section just below it. And in that section, we talk a little bit about shared memory. We have the implementation on the next slide as well. And so I know you've covered a couple different memory management techniques last week, and we had unified memory discussed at the beginning. Shared memory is just another thing to keep in mind that I think is a really cool implementation in Numba. Numba does do transfers of NumPy arrays to the device for us, but if we want to kind of speed up the access to that data, shared arrays or shared memory is one option to do that. It's readable and writable by all the threads in a block. So if we go back to remembering our thread hierarchy, and then since that is the case, the threads can operate together to get towards that one solution at the end. It's basically giving us an opportunity to do manually managed data caching. And then here on the left, I've pulled just a little bit of a snippet of detail from how we actually define the shared array with Numba. We're giving it a shape and type. This is always done on the device. And in return, we get something that is array-like and operates in the same way as our device arrays would if we weren't using shared memory. A common solution or a common technique we have with shared memory in general is having each thread populate one element in that shared array. And then as Chris was asking about at the beginning, we want to make sure we do some sort of synchronization technique at the end to make sure all the threads have finished their work. So matrix multiplication is another one, like Saxby, kind of one of those heavy hitter examples when you're trying to port things to the GPU. This example, and most of these examples are gone over in the Numba documentation, but here is kind of our last all-encompassing problem to look at before we move to the nearest neighbors. You can see we're using CuPy arrays within our Numba kernels. We have the interoperability because we're working within that CUDA array interface environment. And at the top there, we're showing how you would go ahead and actually define the shared array, which again gives us just a little bit faster access to our data. And while the implementation is not something we're incredibly worried about here, it's just a pretty standard matrix multiplication kernel, that we do want to focus on how the shared memory is something that we're getting an added benefit from. We have the CUDA JIT decorator still, so we're doing that just in time compilation. And then on the right, we just have how you go ahead and actually call that function. So this is just kind of an example of the type of lower level detail you can get into when you go about writing your own custom Numba kernels. Here is kind of a summary of the things we've covered so far. This is by no means all the topics within GPU accelerated Python code, but are kind of the heavy hitters. We're focusing really on heavily numerical operations by using NumPy and by virtue CuPy, the GPU accelerated version. And then we have just-in-time kernels available to us on the CPU and on the GPU, which is very useful. So that's what we've covered so far in the Numba section. I realize now we have 15 minutes left in the course, and so I think it will be our goal to cover the introduction to our kind of all-encompassing example, and maybe go over some of the performance benefits that we see when we go through each of the different methods. Does that sound right to you, Chris? We could maybe try to hit one. Okay, I see now. We can try to hit
maybe
like
one slide per
both.
tool.
Yeah, perfect. Are there any questions before we jump into this last example? I think this is a really great opportunity to see the differences in the tools we've covered so far, in turn, the performance benefits we see with each tool also. If there are no questions, we can go ahead and also get started. So we covered it briefly at the top of the talk, which probably seems like a while ago now, but basically what we're going to do is define a problem for ourselves that is just essentially a distance measurement. Why do we care about this? There's a lot of different important tools and things we do that the underlying operation is calculating distance. We have this, we can try to do exact distances, approximate, we can do indexing. Many larger algorithms rely on some sort of distance calculation. We've included a little picture on the top right of a LiDAR open source data set, which obviously relies heavily on distance calculations. And then on the bottom, actually, our own Rapids library uses the Facebook AI similarity search for distance calculations. So wherever you're looking for one, you can find a distance calculation somewhere. We're going to focus specifically on a geospatial workload that we're tailoring kind of to fit not only the size of our GPU, but also to fit the techniques that we want to highlight to you. So here's what we're going to be focusing on today. This is what we're trying to solve. We are trying to resolve geospatial observations to a closest reference point. And we'll go through these images at the bottom that I think are really helpful for describing what that means. But if all we're trying to do is resolve geospatial observations to a single reference point, that's not quite a difficult enough problem to really see the advantages of using the GPU. So we're going to make it slightly more specific and slightly more detailed. What we're going to do is have the observations change as a function of time, which means we could also be getting new observations. And we're going to have our reference points moving at different speeds. So then this means that we're going to have to recompute at every time step. And we want to try to do this at near or real time without having to port our code over to C or C++. So maybe we're all Python developers and we're trying to make this happen much faster without having to go out and have all the overhead of learning C or C++ or porting all of our code there. So what we're trying to do is keep this in Python, get it going as fast as possible. So in the images we have here at the bottom, hopefully you're able to see the observations are the little dots we have, and the colored regions are our reference points. So we're trying to, again, resolve those observations to its nearest reference point within those images. You can see at each time step, they're changing slightly. The dots are harder to notice, but the regions are slightly easier, which goes into kind of the ways in which we tried to make this problem a little more difficult to solve. Here's the high-level algorithm for what we'd be using in most of these solutions. We'll be using the Haversine distance, and at the risk of oversimplifying, that's just the distance on a sphere. And here's what we'd actually be going through as far as the steps in this solution. So we have step one, where we have our input observations, which is our array X, and then we have our reference points, which is our array Y. They could be of different sizes. M and N are not necessarily equal. And then we're going to go ahead and compute a large distance matrix, which is what we're demonstrating in the middle, which is the distance between every X and every Y. And then we're going to go ahead and try to find the minimum there, the closest Y to the first X and the second X, and so on and so on. We want to save the index as well when we find our final solution. So this is what we're going to be seeing in most of the implementations, and what Chris will go ahead and cover now as our first technique. Let's see. Stop sharing. There you go.
There we go. All right, so we're going to compare the CPU and GPU methods for this problem, right? So for the CPU, we're going to first start with a conventional naive double-nested for loop. Next, we're going to move over to NumPy broadcasting. Then we're going to look at using a native scikit-learn machine learning based algorithm, right? So a k-nearest neighbor. And then we're going to look at doing a custom Numba CPU kernel, right? And using JIT compilation. And then for each of those, we're going to use we're going to examine the GPU equivalent, right? So for NumPy broadcasting, we're going to try CuPy broadcasting. For scikit-learn KNN, we're going to try cuML KNN. And then we're going to finish up with a custom Numba GPU kernel, right? You can see the problem size here on the right. Just kind of keep in your mind the idea that the number of observations is much larger than the number of reference points. All right, so to start, right, kind of like the naive, first approach you might do in Python, we have a double for loop, right? So we're looping over our observations, right? And then we're looping over our references, right? And you can see we're using NumPy a little bit here just for the actual data itself, right? And then for each pair between our references and our observations, we're passing them into this Haversine function, which computes that Haversine distance, right? And every single time we compute that distance, we basically check if it's the smallest distance that we've found so far, right? Because we're trying to find the minimum distance for each observation here, right? So at the end, we get an output array that will have for every single observation what the distance is to the closest reference point, and then the identity or the index to the closest reference point, right? This took a really long time. So these are all in the notebook. This one we have commented out so people don't run it on accident. This took around 40 minutes on CPU, and this is probably what people think of when they call Python slow. Right. Good news is we have other options. So running through them here, the first one we could imagine moving over to using NumPy. Right, so the Haversine distance has a lot of trigonometric functions here, right? So we can imagine transforming those from, previously we're just importing them from math. Now we can import them from NumPy sine, cosine, and sine functions. Same for CuPy, right? We can use the GPU accelerated equivalent. And then you'll also notice that we factored out the double nested loop here, right? So in this case, we're taking advantage of a technique called broadcasting, right? Which is a really common method in parallel computing. Essentially, it's a method such that if you're doing an operation between two arrays that are very different in size, it can basically recast the problem so it can be computed in a more efficient vectorized format, right? So one way to see it is here, if we have in a simple case some array X and some other array Y, and we want to add them together, right? As opposed to right, you can do 1 + 2, 2 + 2, 3 + 2, but with broadcasting, that value of 2 is basically stretched out over an array to be an equal size of the other input array, right? So it's kind of ghost and kind of stretched out here, and basically that's an optimization that allows us to do this operation in, again, a vectorized format and get better improved speed at the cost of some additional memory consumption, right? Now this isn't actually replicated, right? In this case, 2 times over and over and over. It's smart enough to know, right, to minimize memory when it can, but in any case, it does come at some memory consumption cost. And you can see here in this case, we're dropping down from 40 minutes or so down to 12 seconds for the NumPy implementation and 277 milliseconds for the CuPy implementation. Moving over, right, so this is a clustering algorithm, right? So there's no reason we can investigate using something like k-nearest neighbors, which is really commonly used in scikit-learn, right? The nice thing here is there's already a really cool API to basically call this function. And you'll notice that, again, the cuML version using Rapids is pretty much identical, right? The API is the same, right? And now we're dropping down to 47 seconds in the case of scikit-learn. And pretty similar in the case, right? Pretty similar to solution to CuPy. We're at 306 milliseconds for Rapids. Okay, now we do have this in the workbook. We don't have time for folks to go through it themselves, but again, you'll have access to this material. Let's go ahead and you just want to briefly introduce the Numbus solution, Zoe.
Yeah, I can go ahead. So we have 2 Numbus solutions that we are going to go through. The first of which, though, is kind of similar to what we are seeing with the double for loop. We're going to go ahead and, this is, I think, the advanced solution. Do you want to just cover this one?
There we go.
Okay, there we go. This hopefully is a little less intimidating than the next slide. The implementation itself, the details inside, should look really similar to what we did again for that double nested for loop. We're just going to go ahead and do that JIT compilation. And we're going to see that when our code is treated as compiled code, we get speedups that are at or near what we see for C or C++. We're down to that 35.4 seconds mark. And basically what we're doing in this Numba example, and I think something we should just keep in mind anytime we're thinking about using Numba, is we're paying a one-time toll to get some pretty fast code with an implementation that is super similar to what you're already working with within Python. We're going to see this in our updated kernel as well, but the syntax will just look a little bit less Pythonic as it does here. So hopefully this looks similar to what we've seen in the past. We're just getting massive speedups when we port over to Numba. So now we can go ahead and look at our final solution if you think that's. So this is a lot of code, and I would strongly urge you to go ahead and take a look at these implementations within the notebook, because I think it is really interesting to look at the differences. A big difference here is that this is not the same implementation details that we had covered in the past. This actually this solution, this custom kernel, takes advantage of the thread hierarchy and the actual GPU layout to get a much, much faster speed up when we do the same calculations as before. So we get down all the way into the milliseconds range. And if I were to try to describe what's happening within these two kernels in a few words, it would mainly be that we have our first kernel in which we're going to try and solve an intermediate solution to this overall problem. So we're going to have a solution for every observation that we have within one block. So if we have 32 blocks, we're going to have 32 intermediate solutions. After that, we're going to make sure to synchronize and wait for all the threads to be done because we have threads doing different work in different blocks. And we're going to solve a similar problem at the end to find our global solution. So overall, what we're going to be doing is we're going to be taking our first 16 threads and our last 16 threads, we're working with 32, finding the argmin and the min value and continuing down until we have one final solution. So at a high level, what we want to highlight here is that when you get down into the weeds of using a custom Numba kernel, the syntax does become less Pythonic and we're required to have an understanding of how the GPU is organized, but we can see massive, massive speed ups. So if this is a huge bottleneck in your program, it's worth the time, I think, to sit down and write yourself a custom Numba kernel using the concepts we covered in the grid. Using the concepts we covered with the thread hierarchy to take advantage of these massive speedups that we can get without actually ever having to leave Python. So this is the final implementation and our fastest implementation. In the next two slides, we have kind of graphics of what they look like. Chris, if you want to quickly go through them, and then we can look at the final comparisons of performance. Yeah, so this is kind of what I was trying to describe, where we have our two-step solution, where we find an intermediate solution per block. We synchronize our threads to make sure everything's on the same page. And then with that final, with those final answers, if we have 32 threads, we'd have 32 intermediate solutions. We can go ahead and find our global minimum solution. And so you can see how this is quite different than the original implementations, but it certainly takes advantage of the GPU architecture in a way that we were in the past. So this is something you can come back to if you choose to go look at that implementation yourself. It is helpful to go ahead and look at a diagram as well. This is showing the same thing. It shows the ways in which we work within a warp, which is just a group of 32. And we do kind of that comparison of the beginning half and the end half, narrowing down until we get our final solution. So this shows how this is a massively parallel problem that we're able to take advantage of the thread hierarchy. So with 5 minutes to go, Chris, do you want to go ahead and compare our final solutions?
Yeah, perfect. Right. Yeah. So yeah, I think you all get the idea, right? It looks more complicated. That's good, right? That expressiveness is showing us all the goodness that lets us get the best, most performant result, right? So this is comparing all the different performance benchmarks again on this test system for the different implementations, right? Again, so that naive double for loop had us at just over 40 minutes. NumPy, even on the CPU, dropped us down substantially down to 12 seconds. And really just with changing that import statement, we're down, really, really big speed up. What is that, 44x there, down to 277 milliseconds. Scikit-learn was a bit worse than the NumPy implementation on the CPU, but I think both of these solutions are very, very comparable on the GPU, right? And both quite a bit faster. And then finally, this is really the crazy one, right? For the Numba kernel, really optimized it very, very carefully with CUDA. You saw we had the warp shuffle in there, right? Really for the expert or CUDA expert, and down to 10.8 milliseconds, right? For our fastest solution there, right? Showing that if it's a problem that you really care about and you can invest the time to optimize it, you can get really good performance benefits. And again, never have to leave Python, right? How nice is that? So a recap of the tools that we use today, right? Hopefully we showed some speedups that were compelling for folks to start using some of these tools, especially when it's so easy to convert them over, right? Especially with some of these drop-in replacements, right? So we talked about Rapids, which includes things such as cuDF for the Pandas user, cuML for the scikit-learn user, and then for the more custom function side, right? If you're a NumPy user doing any numerical computing, you should definitely investigate using CuPy for any of those functions. And then if you need to get more custom and maybe have time to try to crank at it a bit longer and get more performance, that's when you start using Numba. And can't overstate it enough. Numba is really good for the CPU and the GPU, right? The idea of adding in that JIT compilation into the stack really improves performance quite a bit. Want to finish out here by plugging here the GPUhackathons.org organization. So there's actually one of these events going on right now. It looks like I just missed it here on the calendar, right? So there's one going on at SDSC that Zoe and I are both mentoring and having a lot of fun at, right? These events are essentially an opportunity to work with mentors, bring in your application code, right? Maybe it's CPU only, maybe you've done a little bit of GPU programming, maybe you're further along, and sit down with some experts and that will sit with you and profile and help you optimize your code and accelerate your application and get you working on your science more quickly, right? So these are free events and virtual, a lot of fun. And as I said, there's one right now at SDSC. I think there's one coming up at Argonne pretty soon as well. That might be the next one to check out. But with that, yeah, thanks again for the patience as we were running through the workshop, and hopefully everyone learned some useful materials here, and we're happy to take any questions.
Christopher, thanks for the hackathon plug. We'll be doing these every year. And like Christopher said, there's ones that run all year long, and you're welcome to apply for any of them. The concept is the topic might apply to what you're doing. A lot of them are machine learning. We're a combination of HPC and machine learning. And it just might meet your time zone, your travel plans, your home plans, whatever. This year, they're all virtual. I'm hoping next year we'll be in person. That would be really fun. In the fall, we're also going to do our first ever GPU boot camp using the OpenACC hackathon software. So they have some material that we can bring back here, and maybe it will be in person. That would be great fun. And then you could all have this opportunity to train to be mentors at hackathons next year. That's one of the things we want to try and do, is get more people to help other people. So thank you guys so much. We'll reach out to you for other training experiences at our training, and hopefully you can come back next year and we can do this again and maybe update it to H100s.
H100 and 3 hours long.
We might, it's possible we could do the short version and then have a workshop on it. I'd be more than happy to talk with our team, like Susan is here, and it's a matter of time and opportunity, but I would love to do more of this. So thank you, everybody. Any other end of the year, quote unquote, comments or questions? Or I know some of you have reached out to Cindy, who's I think dropped off, about the CCRs if you're a student, and we'll be in touch with you guys about that aspect of the program as well. And Chris and Zoe, he posted their email addresses in there, and that's awesome.
Yeah, you were our alpha testers, so any feedback that you give us will be especially useful on setting the trajectory. We plan to do this quite a bit.
I think I put your emails on the GitHub repo as well. Took that liberty. You are officially mentors. You've been drafted. All right, Susan, I think we could stop recording at this point. Thank you.